term actually. So if you evaluate this term, it will be this thing. F mu nu is the electromagnetic field density, which is related to the electric and magnetic fields. So if you go through this one, and if you also use that gamma I is gamma naught alpha, and that sigma ij, where I and j goes from 1 to 3, is gamma I, gamma I. And if you just make the sum here, mu goes, when mu goes from 0 to 1 to 3. So if you make this sum, and if you make use of these, you will find that this can be reduced to IE alpha I, and also see F0I. Let me also put F0I is delta 0 from this formula, AI minus delta I, A naught. And also you can see that Fij will be So if you do that, then you will get here delta naught AI minus delta I and minus I over 2 sigma ij delta I aj minus delta j. Now you see the meaning is now clear, because this is the electric field, and this is the curl of A. The curl of A is related with the magnetic field. B is equal to curl of A. So you can easily see that what we get here is then the following thing. And let me also write sigma ij, which is, if you evaluate this one here, this you can put as ij sigma k, where sigma k is the diagonal matrix. Okay, now the electric field is minus delta A by delta T minus the gradient of phi as known phi, we have A naught. And the magnetic field is related with that, with the curl of that vector. If I use this identity here, and if I use that thing delta I, this thing here, then these together, you can see, will be, so I can put it like this one, I sigma k delta I aj minus delta aj. And this you can easily evaluate. It's nothing but I sigma k, where B is equal to 30. But this you also can put in terms of the epsilon ijk. It is easy to see that you will get this one here. So our equation then becomes Now I can reduce it into two components, two equations into two components. Spinner. So let me, in Pauli representation, gamma naught is diagonal. So I can write this side as 1 plus gamma naught over 2. Can have two projections here. And this I can write as psi A psi B, where psi will be this projection and the psi B is this projection.
Yes, sir, gamma 0 and gamma 5.
Yeah, gamma naught. Gamma naught. Then I will introduce another representation. So I can have this one here. And this is often written in the literature as psi B for big and S for small. Because if you consider the non-relativistic limit, this will dominate, this will be like, this will be the leading and this will be like O. So this will be S by S. Now you see here, but alpha as you know is 0 sigma 5. So this is non-diagonal. So if I put it into this basis, two component basis, then this psi A and psi B will mix. Okay, because this is non-diagonal and this is diagonal. Every other thing is diagonal, but this is non-diagonal. So this psi A and psi B will mix. So it is preferable then to use chiral representation. Where now in this case gamma phi is non-diagonal, it is 0. So now we take gamma phi to be diagonal. And we take gamma naught to be non-diagonal. And gamma I will make the same. Okay, now I can decompose psi as 1 minus gamma phi over 2. So this will be the left-handed field, and plus we will have here the right-handed field. So this will be sigma L. Now if you remember this alpha I, gamma I, was gamma naught. So that N I will be equal to gamma naught, gamma I. Okay, now you have this gamma naught here and gamma I you have, I think. Okay, anyway, so this will now, this is non-diagonal, this is also non-diagonal, so alpha will be now diagonal. So this will then becomes okay, now this will become diagonal. So alpha I will be now minus 0 minus sigma I. So in this case then, our equation this equation which I have written here will become that if you substitute this one here, so you have here So what you get is that if you expand this, you get delta over delta t plus I e k naught square minus d square. This is the three component minus plus I e sigma dot e minus e sigma dot t plus m square. Now you see psi L and psi are decoupled. So you have equation with psi L with negative sign and with this so psi L and psi are now do not mix, and this is the advantage of using the chiral representation here. Now we can easily interpret this equation. So let me consider two cases. One I will consider here in detail. The other I will give you, because I will not have time to consider that. So let us consider two cases. And one is a pure radiation field. And by this I mean that K is not equal to K naught and we take A independent of time. And then in this case. And then this equation reduces to a very simple part. Minus d square minus e sigma dot t plus m square some psi, where it could be either psi L psi, it doesn't matter because that comes only here plus negative sign. So it is a two-component wave function here. Now you see we want to go to the non-relativistic limit in a way, so no E here the rest energy as E. We can always write in this way the rest energy plus this, where I will take epsilon to be much smaller than m. Okay, now a mode with energy will isolate, as you know, for stationary states, for example. So it will isolate, so psi will minus, so I will write it as minus I E and T. This I separate out from here, and then this will be psi. So it will be psi T. So it has T dependence, but it will be on this one. It will come through this one here, but this main part I have taken out. Now you see, now you see here the derivative comes in. So if I have this derivative here, so I can then so we can write then delta over delta t e is to power minus mc plus the rest of the thing which appears in this equation. So you differentiate it, you get, because it is exponential, it will be the same, so you get minus I m plus delta over delta t acting on the rest. So you do it twice. So we can drop delta square over delta t psi compared to delta psi. So this will be higher order term. As you can see from here, it will involve epsilon square, which I have written there. So I drop it and have only the first order thing. So then this equation takes a simple form. So then we have here e raised to power minus I m t minus m square minus twice I m delta over delta t minus d square minus e sigma dot t plus m square psi. Now this cancel out with this one, so we have a Schrödinger-like equation 1 over twice m from this one here. And if I substitute this, remember d was delta v. And if you remember that, so it is a space part here. So the space part will give you minus del minus R E minus E sigma dot B and psi RT. Now this you can expand. Epsilon psi will give you del square minus I dot D minus I E dot del minus E square. Now you use the vector identity here because it means it is acting on this one, and this you know is now the gauge which I have selected here gives me this 0. So what you get is this A dot delta, so this has been eliminated, so we get minus twice. So the net result is that this del square minus RT square is del square minus twice RE A dot del minus E square. So we get this. So let us take magnetic field B here uniform. Okay. Then the solution B is curl A. So what we need is A. So A you can easily check. This is so is 1/2 E cross R. So this you can easily check. So that we have the A dot del dot del is then 1/2 E cross R dot diameter. And this we can write as 1/2 D dot R cross D. And this you know is the angular momentum. Okay, this is R equal to I over 2 B R cross P. And this you see is orbital angular momentum. So you have I over 2 B dot L. Okay, so we have done here this equation. So let me put it here also. So we have done this equation which I have written here, this equation will then become, if I make use of this one here. So let me write this equation, and now we have done it. So it is minus twice I E A dot del, which is equal to this. If you remember that, then we have this equation. So we have the minus del square over 2 minus E over 2m D dot L, and then we have minus E over 2m. Okay, sigma dot D minus E square. now this is the Schrodinger equation with these two additional terms here. Now this term you expect, because what is this? E over minus E over 2 and is actually the magnetic moment due to the orbital motion of the electron. Okay, so you have this term. Now this, let me put S is equal to 1/2 C. Okay, so then this you would have expected, because due to the orbital motion you have this one magnetic moment. But this is the additional term here. So this additional term, if I put it here, is then I minus T over 2 x twice dot B, then minus this. Now you see, this is the equation which you get here. So this term, as is well known in atomic physics, was verified by the Strasbourg experiment, and this term was needed in the Riemann effect. But in explaining the Riemann effect, people put the spin by hand. Then they didn't know whether they should have here this. Yes, because of that. So then, what they should, in fact, naively you would say that it will be L plus S, that the total angular momentum should come there. But it is not the total angular momentum. It is 1/2. So this factor 1/2 is called actually the magnetic anomaly of the spin.
There's a 2 here. Equal to half E 2 N plus
And
2 N. Actually S is sigma over 2. N plus 2S.
Yes, it is 2. I wrote 2 previously correctly. So L plus 2S. So actually naively you would have expected it's L plus S, but it is L plus 2S. This is known as, in the literature, spin anomaly. Of magnetic moment. Because of this factor 2. Okay, then people have many, you will see a lot of literature on this, explaining this factor of 2. If you see it like some relativistic motion and other things of the electron. But you see here that this factor naturally comes from the Dirac motion. We haven't put the spin, but the spin has come naturally from the structure of the equation itself. And it is actually a great triumph. This is exactly the word which actually Z used for this one, that this is a great triumph of the Dirac equation, that this factor here comes naturally. So this is, in atomic physics, this is known as G equal to. You see, this term you would expect, because this is nothing in classical mechanics. What is this? It is well-known term, the magnetic moment dot B. Okay, so this has to be interpreted. Then the intrinsic magnetic moment of the electron, because this is exactly in the electrodynamics. The magnetic energy is given by mu dot B, where mu is the magnetic moment. Okay, so then we say that the electric has intrinsic magnetic moment, and This is then the operator. And G is 2. So G factor per electron, if you use the terminology of the atomic physicists, G equal to 2. So G equal to 2 is predicted by Dirac theory. What is the experimental situation? So this factor is measured, and just I want to give you the figure, the amazing figure, how accurately this has been measured. Dot 6, 5, 2, 1, 8, 0, 7, 3. Plus minus 0, 0, 0, 0, 0. 0028. Amazing accuracy which has been measured. And if you see the deviation from 1, actually if you write it as 1.001 plus minus the other. So the deviation from Dirac value of 1 is 0.001. Okay, and this has been explained by quantum electrodynamics. And in fact, the quantum electrodynamics, it gives you the radiative corrections to this one here. And if you see there, any book, this will give you 1 plus alpha over 5. So this is the first order radiative correction, alpha over 5, and it's explained the major part of this one. And it has been measured up to 6 order of this. And the agreement between quantum electrodynamics and this value is 1 in million. So it is actually has been verified with this accuracies. So that is why people have so much belief in quantum electrodynamics, because it has been precisely verified in 1 part in million. So this is one success of the Dirac theory. The other is the detail of the hydrogen atom. And this I will not have time to do, but that other case which I discuss here, which I just indicate to you. So that is the Coulomb. Here we consider the radiating pure radiation field. There we consider the pure Coulomb field. So the second case which we can consider is that of the central potential. This is the extreme. And here I put V equal to 0. A equal to 0. And I take so that E minus D the unit vector R, and which we can put as minus okay, so here you have again this which you can evaluate, and then we have D naught here, which we have delta over delta T plus I E naught. Okay, so here the space part will give you simply, because A is 0, the space part will give you simply minus A. Okay, remember now the term which I had there, I alpha dot E, where alpha in the chiral representation is diagonal. So if I make use of that, then this equation becomes here. Minus D in the stationary state, because I will put this delta over delta t as I replace it by IE, okay, the usual case. So we will have minus E square. Now the only part here, the independent part is only here, sigma dot r. Now sigma dot r, if you remember this here, also you see that in Dirac equation which we can easily verify that neither the orbital angular momentum is constant motion nor the spin is a constant motion, but the total angular momentum is the constant motion. Now you see here, so you can use the total angular momentum to identify your states. Now the only part is here, but you see here, if I use this subspace here, I'm just indicating to you here, so this will be J plus minus 1. And if you use this subspace here, then due to the dipole selection rule, this term will have only non-diagonal elements, not the diagonal elements. And this introduce, so all you have to do is to diagonalize a 2 by 2 matrix, and then you can solve it. But I don't have the time. It will take several pages to solve it. But it is easy to solve. But you can see each have followed this approach. There are many approaches. This is this one. Around this material. So you can easily find this one the solution. Now this was again a great triumph because now you see if you actually for hydrogen atom the equation is exactly solvable. It is exactly solvable. That's important. It is only few cases that you can solve the equations exactly, but it is solvable here. But then you will see here that these levels which were degenerate in Schrödinger will split. So in Schrödinger equation you have n square degeneracies. So this will split here, and as it is seen experimentally also. So but the levels here, so these will split, but the other levels, which I think is the 2 is the principal quantum number, and these are the total angular momentum, 1/2 and 3 up, and P is the orbital angular momentum, so it is a P state. But you see the other 2s 1/2. These are still degenerate. So again, as in magnetic moment, one, the main effect is by Dirac theory, the other are radiative correction. So here, this is splitting of the right order as experimentally seen, but this is not split. And this is a famous Lamb shift. So the Lamb shift has been measured, this very small splitting here. And again, Dirac theory actually supplemented with the radiative correction. So QED actually again, you have to do quantum electrodynamics to explain the splitting of these two, and in the famous lab shift experiment. And again, the agreement you will find is 1 part in million. So these are the two successes of Dirac plus quantum electrodynamics, that is, you mix then the quantum theory. Now, the rest of the lecture, I now want to do the invariance of Dirac equation under Lorentz transformation. Again, I will not be able to do full justice of this, but the notes which Dr. Amar Iqbal gave me yesterday actually will cover what I miss here. Okay, so let me introduce the subject here. I could have done this, but it would have taken much longer time. As somebody remarked, the equation can be written in one line, but out of this equation comes the spin of the electron, the tail of the hydrogen atom, and antimatter. Antimatter we will consider when we discuss the whole theory. So let me consider now the invariance. Let me remind you here the famous light principle of special theory of relativity. Actually, just a historical remark, Einstein actually did not get the relativity. He never used Michelson-Morley experiment to formulate his theory of relativity. He used Maxwell equations as a basis for his formulation of the relativity, because Maxwell equations define the speed of light. That speed of light is the same in the vacuum. It has certain value, but it is a universal constant which appears in Maxwell equation. And in Newton's equation you have velocity v, which can take any value, which can be equal infinite, but in Maxwell equations you have this universal constant c. So he based on his relativity on Maxwell equations, but he stated what is called the light principle. And light principle is that the speed of light as measured by all observers is the same. That is to say, that this line is should remain invariant, so this is the universal constant. But you have to put t prime not equal to t. In fact, this was a great barrier, because Lorentz transformation was given by Lorentz much before Einstein, and in fact Poincare agreed essentially what is the special theory of relativity. But they have this mental block that time could be relative. And this mental block was lifted up by Einstein, that time is also relative, and it has to be treated on the same footing as the space and time coordinates. Now this you can write in the following form: c square t square minus x square c square t prime square so this will be an invariant that is in the 4-dimensional notation which I used last time. This interval, which is exactly what this one, should be equal. So a Lorentz transformation is which leaves this interval invariant. So the Lorentz transformation is. So now we want this interval to be invariant. Then there are 2 or 3 intermediate steps, but you can easily verify that because you can write always x mu is equal to g mu x mu and so on. Or x mu as g mu x mu. So if you put it here, there are 2 intermediate steps, but you can see that you must have this condition. So this condition must be satisfied if you want to have the units. Now this is more transparent if I write it in matrix form. In matrix form, this will mean that G is equal to lambda P transpose G. So this will belong to this one here matrix. Now, if I take here determinant of this one, I will get the determinant G which I can write elsewhere because I can which I can also write as if I go to this condition here, because you know that determinant AB is equal to determinant, because it is interchanging rows and columns, etc. So if I make use of this one here, and also you know that this is equal to determinant B. So then this will be equal to determinant G, determinant of lambda, and which you can write as determinant lambda, but lambda, determinant lambda transpose is the same because this is interchanging rows and columns. So this will be equal to determinant lambda square. So what we have is then this condition that determinant lambda square is equal to 1 determinant lambda equal to lambda. So if I take the plus sign, it is called proper Lorentz transformation. And if I take negative sign, it is called improper. Now if the transformation is continuous, if I want to build up from unity by the successive infinitesimal transformation, then I cannot select this one here. This will be a sort of discrete transformation, and so we exclude actually here. So this will be called L plus, and we will exclude this. This will be actually a reflection of coordinates, which I will consider later. So we will exclude this and restrict to L plus. So we will restrict to L plus. Now similarly from this relation you can calculate by calculating V00 from this relation here and making the proper summation, you can show that lambda 00 square is equal to 1 plus sigma I 0 square. And this is, so this will be equal to plus minus or greater than 0. So again we have these two conditions. Lambda 00 either, so this is greater than or equal to 1 from this condition, because that is as I have written there. So either we have lambda 00 so this is, so you have either this condition so you have this condition. So this includes the relative. So we will again limit this cell to this one because that will be the time reversing variance. So we will consider only. So the time reversal, the two discrete transformations we will exclude for the moment. Okay. Okay, so let me just say here, so in matrix form, we have Lorentz transformation. Now lambda is a 4 by 4 matrix. Now it has two submatrices which you can easily see. In fact, you can reduce a 2 by 2 to 4 by 4 matrix into 3 by 3 plus 1, 3 plus 3, 1 plus 1. Okay, so it has two submatrices. Which I can take. I put B for the reason which will come here. So it has these two submatrices. So in other words, this Lorentz group actually has two subgroups. So we have two subgroups, and in fact now this lambda V is what is usually called in the literature. So this lambda V is cosine zeta sine minus canal sine. And this corresponds to Lorentz velocity transformation. And where this, as you know, it's a well identity. And if I put sine is equal to m, x is equal to gamma c, and where gamma is 1 over minus b squared c squared. So your Lorentz transformation will be that. X3 doesn't take part. You can generalize it if you like. That's small. Okay, this is then the usual Lorentz transformation. That is gamma x naught minus d over c x1 and x1 coordinate is gamma x1 minus d over c and then x2 prime is equal to x2 and x3 prime is equal to x3. And this, you know, is the usual Lorentz transformation connecting one inertial frame to the other, which moving with relative velocity v. So here I have taken a particular case and it is moving in the x direction. Okay, so you can generalize it if you like. The other is the rotations. So the other lambda r is cos omega sine minus sine cos. So this is we have x1 prime, x2 prime, x3 prime, and lambda x1, x2, x3, and then we will have here x0 prime, is x0, and x1 prime is x1 cos omega plus x2 sine omega, and x2 is minus sine omega x1 plus x2 plus x2 cosine omega, and x3 prime. So this is then the rotation about the z-axis. So we have actually two subgroups here. One is the usual Lorentz transformation. Now correspondingly we will have two subgroups of the Lorentz group. One will be just SO3, the other will be actually the other one. I will briefly mention it in the next lecture, and then I leave it to the notes of Dr. Ahmed. So the next thing is to identify the generators of this, which we can easily identify. So let me, as the time is now, so let me stop here. And so the important thing is that the Lorentz transformation has two sub-transformation. One is the usual Lorentz transformation, which connects the two inertial frames moving with respect to velocity v. The other is the rotation. Both are combined here.